Hey everyone, welcome back to another topic revision video for CIE A-level physics. Today we're going to talk about the chapter work, energy and power. Now this is a very interesting topic, and this is building on top of the last video that we did that explained a little bit about the work kinetic energy theorem. So a lot of the concepts, especially the transformation between work and energy, you can go through that video and see how we are actually using that. So let's start with the definition of work, or the concept of work done. So the concept is easy to understand. So you can say that this is basically work is done when a force moves its point of application in the direction in which the force acts. Okay, another way you could describe the concept about that is the amount of energy transferred by a force when it acts on an object to move it over some certain distance. Okay, all right. However, this is not the definition yet. So the definition of that is quite specific. It is the product of force and the displacement covered in the direction of force. Now this is the definition that we will have to write if asked in the exam. Now furthermore, if we talk about the mathematical description of this, like the formula, so basically we know that, for example, if we have an object and the force is, let's say for example, going in this direction F, and this is, let's say, this is the positive direction of the displacement. So the work done would be just simply force times by displacement. Let's call it S. Sorry, let's say S. However, if one of the two have an angle between them, so for example, you have this and the force is inclined at, let's say, some angle. The displacement is still in this direction, sorry, X or S in this direction. So since we want the force and the displacement covered in the direction of force, what we will do, force times by S cos theta, or you can say Fs cos theta. Okay, now where we know what force and displacement are. Force, F is force, S is the displacement, and theta is the angle between the force and the displacement. Okay, this we already know the nature of this. Nature of this is just simply scalar. You might wonder why if you haven't studied the vectors topic. So this actually comes about due to the scalar product of the force and displacement. So this is basically due to the scalar product. If you have something like this, like force times by displacement or a length, but the cross product, for example like that, you will have a vector product. Now you might already know what the vector product example is. Moment. The product of force and the distance between the pivot and the line of action of force, that is an example of the vector product. But when you are multiplying force and the length, displacement, whatever you want to call it, and it comes out as a scalar, that is one example is the work. Similarly, the unit for that is joule. J. A common question that could be asked is, express joule in base units. Okay, so let's see how we can actually do that. So we know that 1 joule is coming from 1 Newton of force times by 1 meter displacement, and force, see, work is equal to force times by displacement. Force is basically the kg, meter per second squared, times by meters. So this simplifies to kg meter squared per second squared. Okay, so if, for example, if definition comes for that, also define a joule or something like that. So you could also say that 1 joule is the work done or energy transferred when a force of 1 Newton moves its point of application a distance of 1 meter in the direction of line of action of force. Okay, right. Now let's focus on the force and the displacement, because the dependency is important to understand. So what if the case study, if the force is constant and displacement is variable, and what happens if the force is not constant? So let's see dependencies. Okay, or you can say cases. So when force is constant, okay, so when force is constant, you will have a, for example, let's draw a graph for this. S meters, force Newton. So if this is the case, you will have a graph like this. So the area underneath that graph will be just force times by particular displacement. Just to distinguish between that, let's say, for example, this is x, or let's say, okay, never mind, that's fine still. Let's say this is some specific f, this is some specific x. So work done would be just simply the area under the graph, which is just simply force Fs. However, when force is not constant, again, you can have different cases. If it is, for example, increasing linearly, let's say, for example, let's say you have a linear relationship. Okay, so by linear relationship, what do we mean? Let's say you have this case, F Newton, S meters. Now, there are two examples when this happens. Example number one is where the Hooke's law is concerned. You may be familiar with Hooke's law, although we haven't studied this topic yet. However, this just simply means that this is proportional to extension, or in this case, we can just simply call it displacement also, in the form of extension. Now, when we actually use force and we apply the proportionality, this becomes Kx. K is basically the spring constant. We are already familiar with that. This is an IGCSE O-level stuff, that's why. Now, when we want to find, since now force is a function of x, the work done cannot be just simply force times by x. We have to be a little bit smart about that, because force is not constant anymore, right? So work cannot be just force times by displacement. This cannot work. However, there are two ways to do this. Method 1 is by using area under the graph. Area under the graph. This is the easiest one if you have been able to visualize this as a straight line, force proportional to x. So the area under the graph would be just simply half times by, work equals to half times by force times by displacement. Now, we found in this case, and this is a very particular case, so we're doing that as an example. So force is equal to kx. So when you apply kx over here times by x, this becomes half kx squared. Other method relies on calculus a little bit. So method 2 relies on same area under the graph but using integration. So using definite integration for area under the curve. This is a more generalized expression. Okay, because this expression can be used for anything, or let's say, for example, dx. This now can be applied for even the constant one, the straight line one, for anything, if you know how to use integration. Most of you are doing probably maths A-levels, so you would already be doing this. Now, if we take f is equal to kx, you will get this form. And simple integration we have to do, this would be k. Power is already 1, so we raise the power by 1 and divide by that. Although there will be a plus c involved over here from that, but since we are actually not doing indefinite, we're doing definite between some x1 to x2. x1 to x2. More often we want to know from x is equal to 0, because this is the definition of proportionality. So 0 to x, you will actually just are left with half kx squared, same as what we had over here. Okay, now this was a linear relationship. Okay, another type of similar relationship is the simple harmonic motion, although this is not directly in AS syllabus, but still important. Simple harmonic motion, the restorative force that we have, although this is still equals to mass times by acceleration, but acceleration on the other hand is proportional to minus omega squared. I'm going to write it as displacement, where these two are basically constant. Okay, now basically you can say that minus constant times by displacement. Let's call it S over here. So we will handle it the same way as we did before, by using integral. Sorry, no, ds. So technically, like if you forget the minus sign, the magnitude part of that will still be handled by this thing. So you will actually get a similar answer to that thing. You will have a quadratic expression over here. Now let's move on to the energy part of this topic. Now energy is the capacity of a system to do work. Okay, so for example, we have kinetic, potential, chemical, etc. We are already familiar with the examples. The units for this is same as joule, because as the word suggests, to do work, it's already apparent. Nature of this is the same as the work, scalar. So energy transferred or transformed, either way, this is related to work done. And we're talking about the mechanical work done. However, there are like other changes in energy also. Okay, so we can write it mathematically: change in energy, change in work done. There are several types of energy. We are familiar from the IGCSE O levels also. So for example, kinetic energy. Kinetic means moving. We usually write it as EK, K being the subscript, which is the energy possessed by an object due to its motion Okay, and we are already like familiar with the from the work kinetic energy video how this actually happens. So you can start with the Newton's second law and you will actually get that. So that you can see above the video also, half mv squared, or in this case you can write it as EK. And once again this would be work done, equal to the work done, or just simply work, W. Either way that makes the same thing. Now potential energy we write it as EP, is the ability to do work, or actually sorry, we can rewrite it, we can write it as the energy that an object possesses due to its position or configuration, You can also say that, and it is stored energy it is a stored energy that can be converted into other forms of energy to do work. Okay, so potential, like most common definitions, involve the keywords stored energy possesses due to its position or configuration, but it's important to understand that this potential that we say, potential means potential to do work. Okay, so this means the energy, stored energy that has the potential to do work. We're familiar with gravitational potential energy and elastic potential energy. Elastic potential energy we will see in more detail in the deformation topic. So in this one, let's focus on the gravitational potential energy. For convenience, we will write it as EP also. So it is the energy of a mass due to its position in a gravitational field Another interesting way to define it, you could say that it is a mass ability to do work that results from its position in gravitational field. Now, obviously there is no shortage of the ways we can describe that. So for example, it is the gravitational field between the two objects also that you could say. So another fun way to define this is the energy stored in a system due to gravitational field between two objects. Okay, and that's I think that's more than enough about this. Now, once again, we also studied this in the work kinetic energy theorem video before. I'll put the link above again. That the change in the potential energy, actually let's write it in words, change in gravitational potential energy it comes from the work done against gravity. Okay, so as you can see, this is another form of definition also. It is this mass's ability to do work. It's the energy stored in a mass that results from work done against gravity. Okay, so another way. So that means the change in gravitational potential energy, it actually stems from mg delta h, where h is the change in height, where m is mass, g is the gravitational field strength, Together they combine to become weight, and delta H is the change in height in the gravitational field. Okay, now what we said above is that any kind of potential energy is either due to the work done against energy, so work done against a force is due to the work done against a force, and this will also be equal to the work done when that system is free to move. When object is free to move. Now let me give you an example for example scenarios for both of these. So example 1, where you have, let's say you have an object. We increase the height of this object to over here. So from center to center, let's say you increase the distance delta H upwards. Then you hold it over there. Okay, so the gain in EP, gravitational potential energy, would be equal to the work done against force. Work done against gravity or weight. But once we let it come back to Earth with the same height change, that work done, the loss in EP, or basically the EP itself that we actually stored inside it, will be equal to the work also. So it, as we said before, that it represents the object's ability to do work. So we stored some energy into it by working against another force, and that same force will do work once that system is free to move, and it will result in the same amount of energy change. Furthermore, from the work kinetic energy theorem, any kind of work will also result in change in kinetic energy. So if it's a gain, it will be loss over here. If it's loss, it will be gain in kinetic energy. And in the absence, so one big assumption was that this is in the absence of any air resistance or any other resistive forces also. Okay, so work done results in the change in kinetic energy, and any work done against a force will result in potential energy being stored into the system, and then same potential can be released as work and result in gain in kinetic energy also. Another example is a spring example. Again, this is an example that we will study more profoundly in deformation chapter. So for example, you have this thing and we apply a force that way. Okay, so this way. Now the restorative force of the spring, or the tension force of the spring, is obviously this way. However, let's say you you apply some compression equal to this. So the EP, the gain in elastic potential energy, is actually coming from the work done against spring. spring force, you could say. However, once released, the work, which is the equal to change in kinetic energy, is going to be equal to the same EP that was stored. Elastic potential energy. Okay, so this also, there was a once released. So this exchange of energy is very important. And once again, we are assuming that there are no other, no resistive forces. Now, as we said that these were ideal cases based on conservation of energy, where the mechanical energy, which is the sum of, so let's first write that, so mechanical energy, it is the sum of an object's potential and kinetic energy. And notice that it's not just gravitational potential, it could be any form of potential. So the forces that maintain the balance of conservation, or they conserve the mechanical energy, are called conservative forces. And those that add or take away the mechanical energy, they're called non-conservative forces. But what is this conservation that we're talking about? The ideal case is the conservation of energy. So we are already familiar with the law of conservation of energy, that it states that the energy can neither be created nor destroyed, only transformed from one form to another. Okay? Now, however, an exam-friendly definition or statement is that the total energy of a closed, you can also say isolated system, it remains constant. Okay. Now, in essence, this is describing, both of these statements are describing the same thing that we already studied. For example, one thing that we said, that work done causes a change in kinetic energy. So there is no creation of energy over here, just transformation from one form to another. So work done causes a change in kinetic energy, or change in any kind of energy could cause another form of transformation also. However, this is for like all the total energy, like the sum of all the kinetic, potential, heat, chemical, everything. But in mechanics, we want to know the conservation of mechanical energy, the exchange between the kinetic and potential. Potential, all kinds of potential, not just gravitational, but elastic also. So let's distinguish between the two. So the conservation of mechanical energy. Okay, so there are two types of cases. There are conservative forces. So what are those? As the name suggests, that forces that do not dissipate energy and the work done by these forces depend only on initial and final positions of the object. Okay. For example, we have gravitational force, we have spring force, the restorative force in that. Then we have electrostatic and magnetic force also. And magnetic force also. Okay, and we're mostly talking, the energy that we're talking about is the mechanical energy. So mechanical energy conserved over here. So mechanical energy, which is the sum of kinetic and potential remains constant, which also means that the change in kinetic energy will be equal to change in potential energy. We also studied this in the work kinetic energy theorem video also. So this would mean that the gain in potential energy will be equal to the loss in kinetic energy okay. Similarly, the loss in potential energy will be resulting in a gain in kinetic energy. Now, the other case is when there are applied forces, when the system is not isolated. So this is cases when the system is isolated. Okay. When you have non-conservative forces. Okay, so simply put, these forces add or remove mechanical energy from the system. Okay, so this would mean that, for example, other forces could applied forces. Friction is a very good example, and similarly, air resistance is also a good example. Okay, right. Now, this would mean that the work done by non-conservative forces will include a component of work done also. So the change in potential plus work done will be equal to the change in kinetic. Now we can have the same scenarios over here. So for example, you have let's say loss in potential equals to gain in kinetic. Okay, but for example, the sign of this will tell us whether it's adding to the mechanical energy or removing from it. Okay, so when this, we are already familiar with the work kinetic energy theorem, that if the work is positive, force is in the same direction as the displacement. But if the work comes out as negative, that means force is opposite to displacement, or displacement is in the opposite direction to force. Work done against the force. So over here, for example, this could be if, for example, let's say the work is done against a friction, so you will have a component over here. So for example, work against friction. You could rearrange it into this also. So for example, loss in potential. This is the most common example that comes up, where there is a loss in potential, gain in kinetic energy, but due to the work done against friction, not all of the loss in potential is converted into resistance. Okay, this could be flipped also. Okay, this could be the gain in potential also, loss in kinetic plus work done against the system. Now let's take two examples, although we studied these examples in the work kinetic energy theorem video, but let's take 2-3 examples to understand these two scenarios. So for example, let's say you have inclined plane. This is the one example that we did not do this in that video, and for the same reason, because I wanted to cover it in this one. So let's say you have inclined plane, without friction. Okay, so let's say you have this case over here. There is this object, and the component of the weight, the weight is acting this way. This is the angle theta. The component of the weight that acts parallel to the inclined plane is mg sine theta, and the reaction, and this is the normal reaction force, and this is the component of the weight perpendicular to that. Okay, alright. And obviously, let's say there's a force trying to move it upwards. No friction yet. So, you can do this with the Newton's second law case also, but let's try this with without going to the first principles, but trying the energy method first and foremost. So, if we're trying to move it upwards, that means the displacement is positive upwards, right? In that direction, that means, for example, if the object has covered let's say, let me draw a different diagram over here. Let's say the object has covered from over here to over here, from center to center, let's say some x distance. This is the theta, right? And we want to figure out the kinetic potential energy. So Since obviously it's going upwards, there's a change in height that we need to figure out. So the change in height will come from trigonometry. X sine theta. Okay. So the gain in potential. Oh, well, let's state one condition. Let's say this object is moving with constant velocity. Okay, so this is a big case over here. If this is moving at constant velocity, gain in potential will be equal to the loss in kinetic energy, by the way. Okay, so basically this would be, and since it is constant velocity, right, so obviously loss in kinetic energy would be 0, right? However, this still does not mean that it is not equal to something. It is equal to the work done against gravity. Okay? If you haven't watched the previous video, I'll just explain it quickly. There's an upward force over here minus the mg sine theta equals to ma. Okay? You multiply both sides by the displacement x or s, whatever you want to do that. This side will become 0 because there is no acceleration in this particular case. But this fs minus mg x, or let's say x sine theta, is equal to 0. This would mean that the work done by the force is equal to work done against gravity. So this represents the gain in potential and the work done against gravity. So the change in potential would be equal to work done against gravity, which is the mg delta h, which would be in this case mgx sine theta. What if it's allowed to just fall back down? Okay, moving up. So let's say this case was moving up with uniform velocity. Okay, now let's say moving down, falling back down with weight component as acceleration. So let's see what happens. So same forces are acting over here, same calculation that we will apply over here, but it is now accelerated. So the change in height, the loss in height, would still be the mgh, okay, where delta h is again the x sine theta. Let's say the x covered is this. The force that is actually causing the acceleration is the mg sine theta. Okay, so in this case, the loss in potential energy is equal to the gain in kinetic energy. Again, we have already done the derivation in the previous video, but just to go through that again, just as a recap, there is no force going this way, right? So if we take downwards direction to be positive, you have mg sine theta is equal to ma, but let's write ma as v squared minus u squared over 2s. Multiply both sides by s, you get mgs sine theta, s being the displacement, and this becomes half m v squared minus u squared. Okay, so the loss in EP, gain in kinetic, basically. This represents the loss in kinetic. Since we said this direction is positive, that means this direction will be positive. So the mg loss in height, and this would be half m v squared minus u squared. Now, what if there was friction involved now? Let's say we have the same moving up example but with friction. Inclined plane with friction. Okay, so you have this case over here, and there is a friction involved over here, and once again there is a force driving it upwards, because obviously if we are moving it up, there is going to be a force, okay, and there is going to be a friction. Let's call it Fr. The component of the weight acting is always downwards. Mg sine theta. This is your theta. What else is missing? Change in height. Change in height. Same way as before. Displacement is this. Let's say from this to this, x, one point to another. So without deriving the entire thing again, I think we can do this. But you can do the derivation also. Let's, as a practice, you can do that for first principles. But in the exam, you will need it without this derivation. So you have f minus mg sine theta minus friction. And it depends now if you're moving with constant velocity. Let's say it is moving with constant velocity. So in this case, MA side would be 0. So once you multiply both sides by S, work done by force F would be equal to the work done against gravity plus work done against friction. Okay, so this is your work done against gravity plus work done against friction. That means the total energy provided, for example, if this is the engine of the car, would actually have to supply this much energy. Total work done by force F. Okay, so in this case, this is constant velocity. But what if the body is accelerating upwards? If it's accelerating upwards, there's going to be a change in kinetic energy component also. So if we rewrite this entire thing, the work is going to involve work done against gravity, mg delta h, work done against friction, let's call it work friction, and the gain in kinetic energy, change in kinetic energy. Because we are gaining potential energy also. We're gaining, we're working against friction also. And we're causing an increase in kinetic energy as well. So energy provided by that force would be definitely higher. So in that same case, power provided by the engine would be higher also. Okay, so this is one example how you can try to work with that. Now, speaking of power, its simple definition, that is the rate of work done or energy transfer The unit for this is watt, but you can try doing this in the base units also, which you should, because this could be asked in the MCQs or paper 2 example also. So sorry, this is watt W. So this is let's first write the formula for that. Is power is equal to work over time, or energy per unit time. So for the base units, work is Fs and T, kg, meter per second squared, times by meters, divided by S. So this becomes kg meter squared second per minus 3. So the base units would be this. Okay. Now, if again we had different cases over here where the force is constant, where the force is not constant, same definition, same methodology could be applied to power also. So power when force is constant. Okay, so in this case, when the force is constant, work is simply just Fs. So power, which is your work over energy, work over time, this would be Fs over T, and sorry, force is constant and velocity is constant. When we are talking about this force over here, we're not talking about resultant force. We're talking about a force over here. So constant and constant velocity. Okay, we're not talking about not resultant force. We are just talking about driving force, whatever that is. So as you can see, S over T becomes V, so you can rewrite it as Fv. Okay. Now this could be like a changing velocity also, but force in that case is constant. Now we could be asked about the average power also, in case force is not constant. If force is not constant, and we saw different cases as well for that. So for example, let's say this thing, you have force displacement graph, and let's say for example this could be any non-linear function over here, or linear function also, as long as this is not constant. Okay, so what we would need to do is we need the work or energy, which would come from area under the graph, and divided by time, simply time duration. That will give you the average power. Now there is another scenario also, where power is constant, okay, so the variation of force and velocity, how would that look like? So we need to see, if power is constant, so how would force and velocity would look like? So we know power is related to force times by velocity. So if power is constant, that means that Fv would be constant. which loosely means that force would be inversely proportional to velocity. So how would the graph look like? In this case, a reciprocal graph like this. It's neither of the ends of this graph are going to touch either of the axes. So this is your force, this is your velocity. So over here, this, like how the graph is going, this means that for when you have a constant power supply, either you can increase force or you can increase velocity, but not both at the same time. So when you increase force, you decrease velocity. And if you increase velocity, you have to decrease the force a little bit, if the power supply is constant. And this is the whole argument with the gearing ratios and the speed in the transmission of the cars, basically. Higher gear, lower gear versus higher speed, lower speed. So this is the entire argument of that. Okay. All right. Now, another concept, efficiency. Now, efficiency is also a concept that we have studied rigorously in O-levels or IGCSE. So the definition should be fairly easy to recall. It's the ratio of useful work done to the total energy input. Okay. Now, useful work done, you could also replace it with useful power output or energy output. Energy output. So energy output, energy input would be synonymous. However, the same efficiency could also be written in terms of power also. So ratio of useful power output to the total power input. Okay. So for the first one, if you go with the first one, the equation of efficiency looks like either the useful work done, useful, or any useful energy output, over total energy input. Okay, but if you prefer the power argument, both of them are correct, but it depends on question to question what do we have to use. So useful power output and the total power input. Okay, and the question may ask to give the efficiency as a percentage, so you can just simply multiply this by 100%. Now, a familiar diagram which you may already remember from IGCSE or O-levels or in the books are Sankey diagrams, which are a very neat way of showing efficiency. So the widths, basically these are just arrows. So the width of those arrows tell us how efficient a system is. So for example, like this, and let's say like this. Okay, so like this, and okay, so this would represent the useful output, whatever this is, energy, power, whatever this is, and this is energy lost or power lost, lost energy or power. So useful output energy or power. The width, for example, if this is, let's say we have like drawn it like 5 divisions over here, 3 out of 5 would mean 3/5 times by 100, sort of like 60% efficiency, and this would mean that 40% is lost over here. So 2/5, for example, we made it this way, so 40% is lost. All right. Now, before we go to questions, there's one little derivation that could be asked, is derive an expression of kinetic energy in terms of momentum. Okay, so we know that momentum is basically product of mass times by velocity. So if we square both sides, you get p squared equals to m squared v squared. Okay, kinetic energy, on the other hand, we know that this is half m v squared. So if you notice the similarity over here, there's only like one m missing over here, so we can rewrite it as half m squared v squared over m, right? So this would cancel out one of the m's. So m squared v squared is your p squared, momentum squared over m. And that's your minor derivation. Okay, so let's see some questions. Alright, so let's try some questions. A ball of mass m is thrown up to a height h in air with an initial velocity v as shown. Air resistance is negligible. The acceleration of free fall is g. What is the total work done by the gravitational force on the ball during its flight from P to Q? Since the net change in the height is 0, the total work done by gravitational force on the ball would be 0 also. But if you'd like to split it up, going upwards, the work done by the gravitational force would be negative. Okay, because the displacement is opposite to the force, because force is downwards. However, the coming down motion, falling back, that is going to be work done by the gravitational force. That is the mgh also. However, notice the wording that they used over here and with the sign convention that we are using over here. They're not saying change in gravitational potential energy. They're saying total work done by the gravitational force. Okay, if we were talking about the change in gravitational potential energy going up, that would be positive mgh, and coming down it would be negative mgh. But total in this case, this is called work done against gravity. But the question is actually asking total work done by the gravitational force on the ball. Okay, so that would be negative, positive. So net work done is 0. What is the definition of power? This is easy, work done per unit time or energy transferred per unit time. Not 1 second, not second, in unit time, no. Per unit time. A model car travels at a constant velocity of 12 meters per second in a straight horizontal line. The input power to the engine is 800 watts. Efficiency of the engine is 60%. What is the total horizontal resistive force on the car? Okay, so if the input power is 800 and 60% only is used to provide the forward power, so that means the 60% times by 800 watt is your FV, which is your this. So 800 times by 0.6 divided by 12, 40. Which statement represents the principle of conservation of energy? Energy cannot be used faster than its greater. No. Supply of energy is limited, so energy must be conserved. No. Total energy in a closed system is constant. That is correct. Closed system is basically a system where mass cannot be changed. There's no give or take or mass, but there's a give and take of energy and work. So total energy of that closed system would be constant. That means there could be transformations of energy inside that particular system. A barrel of mass 50 kg is loaded onto the back of a lorry 1.6 meters high by pushing it up a frictionless plank 3.4 meters long. What is the minimum work done? Okay. Now, minimum work done is basically the work done against gravity, which is just simply mgh. Why minimum? Because if we start to consider the change in kinetic energy, then the work done would be greater. If there is a change in kinetic energy, the work done would be greater. So, if there is no change in kinetic energy, if the change in kinetic energy is 0, then work done is the change in gravitational potential energy. If, however, that is not the case, the general form would be that it is greater than the change in this. Or you can say equal to change in gravitational potential energy and change in kinetic energy. And you can see the entire lecture for this. And also the work kinetic energy theorem video. So in this case, the mgh is 50g plus, that is the minimum work done. So that is 50 times by 9.81 times by 1.6. 50 times by 9.81 times by 1.6, 784.8. To two significant figures, it would be 780. A stone of mass 0.3 kg is thrown vertically downwards with a speed of 20 meters per second from a height of 12 meters above the ground. It falls vertically until it hits the ground. Air resistance is negligible. What is the kinetic energy of the stone before it hits the ground? Okay, there are two ways we could do this. By using kinematics. First, we find out the final velocity using kinematics. The other method is just simply using the energy method. Okay, so the simple diagram for this is that the object is falling with initial velocity 20 meters per second, and to find out the kinetic energy falling on the ground before it hits the ground, we actually need to find out the final velocity. And this is 12 meters. Okay, so let's say, for example, we just use kinematics to find v or v squared, either way. So since we have displacement, initial, final velocity, and acceleration is 9.81 meters per second squared, so we can use this thing. So v squared would be 2gs plus u squared. So this would be 2 times by 9.81 times by 12 plus 20 squared. So you get 2 times by 9.81 times by 12 plus 400. This is your v squared. Okay, 635.44. When you multiply the half and m with it, half times by m is 0.3 times by v squared, which is 635.44. Right, okay, so we save this, times by 0.5 times by 0.3, this is 95.3. Now, What is the other method? By using simple energy method. Using energy method. So what we're going to say is that the change in gravitational potential energy is equal to the change in kinetic energy. Or you can also write it as the loss in EP is the kinetic energy gain. So mgh, right? mm on both sides would be same, so but still we can rewrite it. 0.3 times by 9.81 times by 12 equals to, now change in kinetic energy, so half times by 0.3 times by, actually we need the final kinetic energy, right? So we can leave it as EK final, or EF for energy, kinetic energy final, minus kinetic energy initial, half m v squared is 20 squared. So your kinetic energy final would be 0.3 times by 9.81 times by 12 plus 0.5 times by 0.3 times by 400. As you can see, we are getting the same answer as before. So 95 would be the correct answer. A student can run or walk up the stairs to her classroom. Which statement describes the power required and the gravitational potential energy gained while running up the stairs compared to walking up them? Okay, so one thing you have to remember, that the change in gravitational potential energy would be the same for walking up the stairs and running up. Okay. However, for running will require more kinetic energy. Running uses more kinetic energy. Hence, more power would be required. Hence, more power required. Okay. So we just have to find these conditions. So same gravitational potential energy. That means these two will just be eliminated. Uses more power. This one would be correct. Okay. The weight W hangs from a trolley that runs along a rail. The trolley moves horizontally through a distance P and simultaneously raises the weight through a height Q. As a result, weight moves through a distance R from X to Y. It starts and finishes at rest. How much work is done on the weight during this process? Okay. So if you see this over here, that the force acting on this object, weight W, whatever this object is, force on this is always upwards. Okay, so it's technically just moving upwards, but it's the motion of the trolley that's just making it seem like it's moving towards the right. But force on this is never towards the right. It's always upwards. That means the tension force, if it's moving with, let's say it starts and finishes at rest, that means that the net, like, kinetic energy would be 0. So that means the net work done is just the change in height. So this thing, there is no force acting on the weight parallel to this direction. It's only in this direction. So it's just mgh w q. Okay. The equation for kinetic energy Ek can be derived using equations of motion. We already saw that. We need the Newton's second law, F is equal to ma. We need the v squared minus u squared over 2s, equations of motion. And we also need the work is equal to Fs. So this one, this one, this one. 1, 2, and 3. If you want to see how to derive this, you can go through our work kinetic energy theorem video. A box of weight 40 Newton is pushed with a horizontal force of 20 newtons along a level ground for a distance of 2.4 meters. The box is then lifted at constant velocity through a height of 1.6 meters by a vertical force. What is the total work done on the box by the two forces? Okay, so the total work would be the work done against friction. No, sorry, not against friction, is by the horizontal force. Horizontal force plus work done against gravity. Okay, so this would be 20 times by 2.4 plus 40 times by 1.6. So 20 times by 2.4 plus 40 times by 1.6 is 112, which would be this thing. Which statement about the efficiency is correct? It does not have a unit, so that's basically simple answer. The force resisting the motion of a car is proportional to the square of the car's speed. The magnitude of the force at the speed of 20 meters per second is 800 Newton. So basically they have said that the force resisting the motion is proportional to v squared, square of car speed. What useful power output is required from the car's engine to maintain a steady speed of 40 meters per second? Okay, so first off we need the force, right? So that would be, F over, let's say, 800 is equal to 40 over 20 whole squared. So 20 times by 2 squared, 4 times by 800, that is actually 3200. Now this is just the force, this is not the speed, this is not the power. To do that we need to multiply this by this, so 3200 times by 40. So the answer is simply, we know 32 times by 4 is 128, so 128,000. So 128 kilowatt would be the correct answer. Okay, let's move on. A box of weight W is pulled by a force P along a slope. The length of the slope is D and the box rises a height H. Frictional force between the box and the slope is F. The diagram shows the directions of the forces. The purpose of the slope is to raise the box vertically. Okay. So this means that in the energy terms, the work done by, see P is the input basically, right? However, we need to see what are the total work. So if the purpose of the slope is to raise the box vertically, so the energy output basically is the mgh, which would be wh, divided by the total energy input that is coming from P. Okay, now technically, like for example, if you just say WH plus FD, you wouldn't be very wrong. However, we don't know what the situation is between the magnitudes of forces. We know that it is moving up. This would make sense if P is equal to the mg sine theta plus F. That means if it's moving with constant velocity, but we don't know that. We do know that P is the force that is being applied. So the work done by P is actually the input but the work output is WH. So D, the simplest explanation. Okay. The kinetic energy of the particle is increased by a factor of 4. By what factor does the speed increase? We already know this answer, that kinetic energy is proportional to v squared. So if it's increased by a factor of 2, that means 4v squared. The EK increases by 4. So just 2. This is easy. This is, what is the, okay. In many filament lamps, as much as 92 joules of energy is emitted as thermal energy for every 8 joules of energy emitted as light. Efficiency, obviously, as a percentage of energy electrical converted to light energy, right? So that is the efficiency, right? So 8 over 100, because 92 energy is emitted as thermal, 8 as this, so just simply 8%. What is the unit of power? Watt, but is also joules per second. Okay. Alright. An object is in a uniform gravitational field. The graph shows how the change in gravitational potential energy EP of the object varies with distance x moved by an object from a fixed point. EP. So this actually tells us that the EP, change in EP, is proportional to x. We already know that EP is basically the change mgx. Okay, so basically like the EP change is your mgx. So this equation basically tells us everything. However, since it is proportional, this means that this part over here, which is the force, that is constant, which means that the force to distance relationship would be constant also. Alright, a block of mass 2 kg is released from rest on a slope. Released from rest, that means U is equal to 0. It travels 7 meters down the slope and falls a vertical distance of 3 meters. The block experiences a frictional force parallel to the slope of 5 newtons. What is the speed of the block after falling this distance? So over here, since there is a frictional force, the change in gravitational potential energy is equal to, you can say, the loss in EP also. We can say that. Let's make that this way. Loss in EP is equal to gain in kinetic energy plus work against frictional force. I'll just write it as VWF. So loss in EP is 9.813. Since it is released from rest, so U squared would be 0, so half m V squared plus work done against frictional force, 7 times by 5. Okay, so this cancels out with this, so 2 times by 9.81 times by 3 minus 35, that is your V squared. So V would be 4.88, which is roughly 5 or 9. 4.9, sorry. 8. Okay. Alright. We don't have to do every question, but at least something. Let's see this. A crate of mass 50 kg is pushed a distance of 6 meters along a horizontal surface against a constant resistive force of 70 newtons. Crate moves at constant speed. It is then lifted at constant speed through a vertical distance of 1.2 meters on the back of the lorry. What is the total work done in the process? So total work done will be work done against frictional force or resistive force, sorry, plus work done against gravity. Okay, so in this case, this is 6 times by 70 plus 50 times by 9.81 times by 1.2. So 60 times by 70 plus 50 times by 9.81 times by 1.2, 1000 joules. Right, okay. Let's see this one. An electric car travels at a constant speed of 70 kilometers per hour for 80 kilometers on a straight horizontal route and uses energy E from its battery. Total resistive force acting on the car is proportional to speed squared. Assume that the electric motor is 100% efficient. How much energy is used from the battery when the car travels at a constant speed of 60 km per hour for 80 kilometers on a straight horizontal road? So, the question may sound a little bit confusing where the distance is given, speed is given like this. However, all we need to know is energy is basically E is equal to PT, which is FVT, and your VT is Fs. S we already know, we need to find out F, okay, or the expression for F. So when we have 70 kilometers per hour for 80 kilometers, so we know that F is basically proportional to V squared. So this is some K multiplied by V squared, which is 70 squared. Okay, we can keep it in the form of kilometers per hour. There is absolutely no difference to that. So let's call it F1. F2 on the other hand would be K, same K, times by 60 squared. So basically what we would have done the otherwise also, so basically when we divide both of these things, K and K would just cancel. So your F2 is basically 6 over 7 whole squared times by F1. Okay, so 6 over 7 whole squared, so 36 divided by 49. So this is, actually we can keep it like this, we don't need to do anything for that. Okay, however, the energy used before is F1s, which is just simply F1 times by 80 kilometers. Because V and T, they would just simply make displacement E1. E2 is your F2 times by the same distance. So your 36 over 49 F1 times by 80. So you see F180 is your E1, or E in this case. 36 over 49, that is 0.73. So your energy 2 is actually 0.734 or 5 previously. So A is the answer. What is meant by the efficiency of a system? Useful energy output of the system divided by the total energy input to the system. That's it. Okay, let's try out some difficult question. Okay, let's see this one. A man sits on a buggy that is pulled along by a wire attached to a kite. Wire is at an angle of 40 degrees to the horizontal and has a constant tension of 200 newtons. The man and the buggy travel a distance of 20 meters along a straight horizontal path. The wire and the path of the buggy are in the same vertical plane. What is the work done by tension force on the man and the buggy? So this is easy. force in the direction of the displacement is just 200 cos of 40 degrees. So work done would be just simply 200 cos of 40 degrees times by 20. So 200 times by 20 times by cos of 40. So 3000 or 3.1 kilojoules. That's okay. All right. The ball is thrown vertically upwards from the surface of the earth. Which statement describes the energy of the ball as it rises through the air? So kinetic energy is decreasing and potential energy increasing. Total energy can never increase. Okay. In the free fall case, in the absence of any other applied forces, total energy cannot increase. It can decrease due to resistive forces, but not increase. Kinetic energy of the ball increases as the gravitational potential decreases. No, it's the other way around. Kinetic energy of the ball decreases as the gravitational potential energy increases. So this is correct. And what is the efficiency of the turbine? Power output over power input. I think we can move on to paper 2 questions now. Oh no, this is just forces. Okay, let's see this. An airport has a mechanical system for moving luggage. The system uses a horizontal conveyor belt, a sloping conveyor belt, a lift, and a frictionless slide. Suitcases move around the airport using the system. Okay, there's a conveyor belt, sloping conveyor belt, a lift, and a frictionless slide. Okay. Resistive forces opposing to the motion of the suitcase are negligible. Okay. For which movement of the suitcase is the net work done on the suitcase greatest? Moving the suitcase a distance of 8 meters at constant speed up the sloping conveyor belt. This would be, for example, if this is just mgh, this is just 8 mg. Okay, we can figure out in a second. Moving the suitcase a distance of 16 meters at constant speed along the horizontal conveyor belt. Whatever this force is, force times by 16. Okay. This is mgh again. 10 mg. Moving the suitcase a distance of 12 meters at increasing speed downwards on the slide. Okay. At increasing speed down the slide. That means they are providing or increasing the kinetic energy of the system. So there is a loss in potential energy, but there is a gain in kinetic energy also. Alright. To answer this, you have to understand what they're asking. For which movement of the suitcase is the net work done on the suitcase greatest? So over here, the constant speed, that means there is no change in kinetic energy. So potential energy is the only thing that is increasing, 8 mg. The net work done on this case would be, you see, it has no, how do we explain this? There is no change in potential energy, there is no change in kinetic energy. Over here, there may be no change in kinetic energy, but there is an increase in potential energy. Over here, the change in gravitational potential energy is countered by the change in kinetic energy. So C is the answer that makes the most sense. Okay. Let's see. An object of mass 0.4 kg is projected into the air, follows a curved path above the horizontal ground. The object takes a time of 1.5 seconds to move along its path. Object lands a horizontal distance of 18 meters from its initial position. Air resistance is negligible. What is the kinetic energy of the object at its maximum height? Now this is a very simple question. It is landing at the same level back over here, so that means the net displacement is 0, and at the highest point it will be exactly half this point. So at 0.75 seconds it will be at its maximum height. Furthermore, the kinetic energy at its maximum height is just due to its horizontal velocity. Okay, so we just need the horizontal velocity. Sx is equal to uxt. So we are already given this. So 18 meters divided by time 1.5, that is your horizontal velocity. 18 divided by 1.5, this is 12. So kinetic energy would be just due to this. So half m v squared. So 0.5 times by 0.4 times by 144, 28.8, 29 joules. Okay. Alright, let's try some paper 2 questions. State what is meant by work done by a force. So this is simple. It is the product of the force and the displacement in the direction of force. Okay. Alright. A block of mass m is raised vertically at constant speed. Vertical height gained by the block is delta h. Derive an expression in terms of m delta h for the change in gravitational potential energy, EP, of the block. State the meaning of any other symbols you use. Okay. So, for example, it is being lifted up. So, force, there's a weight downwards. This is mg downwards, right? So, lifting force F minus weight mg is equal to ma. Okay, so any other symbols we use? So a is acceleration, okay, and g is the gravitational field strength, or gravitational acceleration due to gravity. Sorry. Okay, so we have this. A is 0, so when we multiply force minus mg equal to 0 times by delta h, you get Fh is equal to mg delta h. So your work done against gravity is equal to change in gravitational potential energy is equal to mg delta h. An electric motor has an input power of 900 watt. Motor takes 1 minute to lift a load of weight 240 newtons at constant speed through a vertical height of 150 meters. Resistive forces are negligible. Show that the work done by the motor on the load in the 1 minute is 36 kilojoules. So basically the lifting part, mgh, this is mg is already given 240 and height lifted is 150. So 240 times by 150 is 36,000. We already defined it that the work is the change in gravitational potential energy. So this is 36 kilojoules. Determine the useful output power of the motor. So the work divided by time, work done, divided by time. So 36,000 divided by time was 1 minute, right? So 60 seconds. So 6 times by 6 is 36, so 600. Use your answer in C to determine the efficiency of the motor. So input power is 900, so efficiency would be 600 over 900. This is just simply 2 over 3, 66. So either you can write it as 0.67 or you can write it as 67%. Okay, all right. Define momentum. It is the product of an object's mass and its velocity. Okay. A child stands on a scooter on a horizontal ground. The combined mass of the child and the scooter is 16 kg. Child starts from rest and pushes on the ground with her foot, which causes her to accelerate. Push lasts for a time of 1.1 seconds. Speed of the child and the scooter after the push is 0.6 meters per second. Determine the average resultant force on acting horizontally on the child and the scooter during the push. Okay, so we know that force is the rate of change of momentum. So change in momentum is 16, final speed is 0.6, initial speed 0, time duration is 1.1. So 16 times by 0.6 divided by 1.1 is 8.727 newtons. Later, the child in B travels down a slope at constant angle to the horizontal as shown in figure 2.1. At point A, her speed is 0.6 meters per second. She has a constant acceleration of 0.85 meters per second squared parallel to the slope. After a time of 3.7 seconds, she reaches point B. Calculate the distance x traveled by the child along the slope from A to B. This is just simple kinematics. So S is equal to ut plus half at squared. So therefore this is x. U is 0.6 times by 3.7 plus half times by 0.85 times by 3.7 squared. So 0.6 times by 3.7 plus 0.5 times by 0.85 times by 3.7 squared. So 8.038, which is just 8.0. Okay, at point B, the child in C applies the brake with constant force to maintain a constant velocity. Point C is 18 meters from point B as shown in figure 2.2. The work done by braking force between B and C is 250 joules. Determine the magnitude of the braking force. The work done is your force divided by displacement. The work is 250 and displacement covered is 18. So 250 divided by 18, the braking force is 13.889. So 13, let's call it 14. On figure 2.3, sketch the variation of the kinetic energy of the child and the scooter with distance traveled from point A to C. Numerical values for kinetic energy are not required. Okay. So from A to B, this person is accelerating uniformly, right? However, notice that this is not the kinetic energy with respect to time. This is kinetic energy with respect to distance. So in this case, ut plus half at squared. Sorry, not time. You can say 2as v squared minus u squared. So in the first part, u is 0. So your s is basically proportional to v squared. So proportional means straight line passing from origin. But after from B to C, the kinetic energy is constant because it's maintaining a constant velocity. So your kinetic energy would be constant. And that's about it. Right? Let's see more. State what is meant by center of gravity of an object. A point through which line of action of weight appears to pass. Or you could say a point through which entire weight of an object appears to act. Okay. Two blocks are on a horizontal beam that is pivoted at its center of gravity as shown in figure 2.1. Now if it's if it's pivoted at the center of gravity, that means center of gravity or the weight will not have any moment about the pivot. A large block of 54 newtons is at a distance of 0.45 meters from the pivot. Small block of weight 2.4 newtons is a distance of 0.95 meters from the pivot and a distance of 0.35 meters from the right hand end of the beam. Right hand end of the beam is connected to the ground by a string that is an angle 30 degrees to the horizontal. Beam is in equilibrium. By taking moments about the pivot, calculate the tension T in the string. Okay, so the component of tension perpendicular to the distance that we have is your T sine of 30. So since it is in equilibrium, sum of moments is 0. Algebraic sum of moments is 0. So your 54 times by 0.45 is equal to 2.4 times by 0.95 plus 0.95 plus so 0.95 plus 0.35, 1.3 times by T sine 30 degrees. Okay, now we just need to find out T. So T would be 54 times by 0.45 minus 2.4 times by 0.95 divided by 1.3 sine of 30. Sine of 30 is just 1/2. So 54 times by 0.45 minus 2.4 times by 0.95 divided by 1.3 sine of 30 degrees. So we can just call it 34, 33.8, 34, let's call it. Okay. String is cut so that the beam is no longer in equilibrium. Calculate the magnitude of the resultant moment about the pivot acting on the beam immediately after the string is cut. So the moment is just due to this thing. The net moment, the resultant moment would be just equal to this thing or the difference between these. So all we need to do is to just divide this by 1 and we will get our answer. So T sine 30 degrees times by 1.3 is the same. We will get the same thing. So 22.02 or just 22. Right. The beam in B rotates when the string is cut and the small block of weight 2.4 newtons is projected through the air. Figure 2.2 shows the last part of the path of the block before it hits the ground at point Y. At point X on the path, block has a speed of 3.4 meters per second and is at a height of 1.8 meters above the horizontal ground. Calculate the decrease in gravitational potential energy of the block for this movement from X to Y. So this is like easy. So mgh. So mg is already given, 2.4 times by 1.8. Right, okay, 4.32. Use your answer in C1 and the conservation of energy to determine the kinetic energy of the block at Y. So, we already know that the loss in gravitational potential energy is equal to gain in kinetic energy. There are no air resistance, right? So, this is the conservation of energy principle. So your mgh that we have actually found, 4.32, is your gain in kinetic energy. So 4.32 is equal to, we need the kinetic energy of the block at Y, so we will just leave it as Ek minus half. M is 2.4 divided by 9.81 times by V squared. They gave us 3.4 squared. Okay, so 4.32 plus 0.5 times by 2.4 divided by 9.81 times by 3.4 squared. 0.5 times by 2.4 divided by 9.81 and times by 3.4 squared. So this is your kinetic energy after, so this is 5.7. State the variation, if any, in the direction of the acceleration of the block as it moves from X to Y. No change as the acceleration acts downwards. As direction of acceleration is due to weight or gravity. Okay. The block passes point X at a time Tx and arrives at point Y at time Ty. On figure 2.3, sketch a graph to show the variation of magnitude of horizontal component of the velocity of the block with time from Tx to Ty. So this is simple kinematics. In projectile motion, initial velocity remains constant. So horizontal component of velocity would remain constant. Alright, let's see this one. Alright. A motor uses a wire to raise a block as illustrated in figure 2.1. Okay. The base of the block takes a time of 0.49 seconds to move vertically upwards from a level X to level Y at a constant speed of 0.64 meters per second. During this time, the wire has a strain of 0.0012. Wire is made of Young's modulus. This and has a uniform cross section. The block has a weight of 1.4 10 raised to power 4. Assume that the weight of the wire is negligible. Calculate the cross-sectional area of the wire. Okay, so we know that Young's modulus is stress over strain. So stress is basically the Young's modulus times by strain, and this is just force over area. So therefore the area, cross-sectional area, would be force over Young's modulus times by strain. So force is equal to the weight, tension 1.4, 10 raised to power 4, divided by Young's modulus 2.2, 10 raised to power 11. Strain is 0.0012. So 1.4 divided by 2.2 divided by 0.0012 times by 10 raised to power 4 minus 11. So 1, 2, 3, 4, 5. The increase in gravitational potential energy of the block for the movement of its base from x to y. So how much distance did we raise it? We don't know that, but we do know the time and the velocity. Okay. So change in gravitational potential energy would be mg, that is 1.4, 10 raised to power 4. Change in height, constant velocity, time, vt, 0.64 times by 0.49. So 1.4 times by 10 raised to power 4 times by 0.64 times by 0.49. 4390.4. So let's call it 4400. Right. The motor has efficiency of 56%. Calculate the input power to the motor as the base of the block moves from x to y. So basically that means we first need the power output. Okay, without that we cannot do that. So power output is the work done over time. Work done, we just calculated it to be 4400 divided by time. This was 0.49. 49 or 64? 49. Okay. So 4400 divided by 0.49. So this is 8979.591 watt. So power input would be equal to power output divided by efficiency. So 8979.591 divided by 0.56. So this divided by 0.56. This is 16,000. So roughly 16,000 watt. The base of the block now has a uniform deceleration of magnitude 1.3 meters per second squared from a level y until the base of the block stops at level z. Okay, from level y, level z, constant deceleration. Calculate the tension T in the wire as the base of the block moves from y to z. Okay, so if we just draw the free body diagram, there's a weight acting downwards. Tension is upwards. However, the acceleration upwards is negative 1.3 meters per second. So if we write it as T minus mg, we will have to write m minus a. Okay, so this would mean that you could do the mg minus also. So mg minus t is equal to ma, where in this case a would be just 1.3 and over here we can use minus 1.3. Alright, so a is 1.3. Either way you will get the same answer. So since we want t, I wrote it this way. So this would be mass is, they gave us the mass. Sorry, no weight, they gave us the weight. 1.4, 10 raised to power 4. Okay. 9.81 times by minus 1.3 plus mg is just weight. So this. Okay. So 1.4 times by 10 raised to power minus 4 times by minus 1.3 divided by 9.81 plus 1.4 times by 10 raised to the power 4, we get 12,000. So 12,000. The two significant figures. The base of the block is at levels x, y, and z at times tx, ty, tz respectively. On figure 2.2, sketch a graph to show the variation with time t of the distance d of the base of the block from level x. Numerical values of d and t are not required. Okay, so from x to y, it is moving with constant speed, right? So it is moving with uniform velocity. But from y to z, it is moving with deceleration. So actually, sorry. Okay, let's try again. So okay, and then it's decelerating, so it will go this way. So the distance is still increasing, but the velocity is decreasing. So as you can see, the gradient of this will start to decrease. Alright, so let's see the next question. Let's find an interesting question. Okay, this is an interesting question. Okay, define power, that is the rate of change of energy or rate of work done or energy transfer with respect to time. Okay. The mechanical power P can be calculated using the formula P is equal to Fv. Use the concept of work and definition of power to show how this formula is derived. Okay, so how they've actually phrased the question, we can't just simply derive it with symbols. We need the concept of the work and the definition of power. So your work is force times by displacement. Okay, power is your work divided by time. Okay, so this would mean that this is your force times by displacement times by time. Okay. Now velocity is displacement over time. Hence, power is force times by velocity. So in symbols, P is equal to F times by V. So you can add symbols over here. So W work, force F, displacement S, power P. Actually, it should be on the right hand side, but work time, force F, displacement S, time T, velocity V, displacement S, time T, power P, force F, velocity. That's it. The engine of a lorry provides 130 kilowatts of power to lorry's wheels when it is traveling at a constant speed of 25 meters per second along a straight horizontal. Show that the resistive force opposing the forward motion of the lorry is 5200 newtons. Okay, so basically what this means is that the lorry is traveling forward, so obviously there is going to be a driving force also, and there is going to be the resistive force. Okay, since it is moving at constant speed, since acceleration is 0, driving force is equal to resistive force, which would also mean that the work done by the driving force, or by the engine, let's say, is equal to work done against resistive force. Okay, and this would be and we also know that the power is equal to force times by velocity. Okay, so this same argument can be written in the form of power also. Okay, so therefore force would be power against resistive force over velocity. So this is 130,000 divided by 25. So let's plug in the values. 130,000 divided by 25. We get 5,200. Alright, let's move on. The lorry in B travels up a straight section of a road that is inclined at an angle theta to the horizontal. The lorry has mass m and the acceleration of free fall is g. Determine an expression in terms of m, g and theta for the component of the weight of the lorry that acts parallel to the surface of the road. So this is very easy. It's just mg sine theta. The total resistive force remains unchanged at 5,200 newtons, and the engine now provides greater power to maintain a speed of 25 meters per second. The total mass m of the lorry is 36,000 kg. The angle theta is 1.4 degrees. Determine the power in kilowatts now provided by the engine. Okay. Now, what we actually had that the constant speed was 25 meters per second. Okay. And there is a component of the weight, that means there is some work done by gravity also. There is no change in kinetic energy, right? So the power supplied by engine, power supplied by engine is used against power against gravity plus power against resistive force. Okay, so power against gravity, this would be, we need to figure out the work time, right? Or just simply Fv, right? So Fv, we just wrote it mg t sine theta, right? So m is 36,000. G sine 1.4 degrees times by velocity 25 plus 5,200 times by 25. Okay, and we need it in kilowatts. Alright, so first let's find it out in watts, and then we can convert it. Times by sine 1.4 times by 25 plus 5,200 times by 25. So we get this. 345,711.7. So in kilowatts, this would be roughly about 350 kilowatt. Okay, so to two significant figures. Alright, so let's move on. Let's see some interesting question. Okay, we can do both of them. Alright. An archer releases an arrow towards a target at a velocity of 65 meters per second at an angle of 4.3 degrees above the horizontal. When released, tip of the arrow is a horizontal distance of 70 meters from the target and 1.66 meters above the horizontal ground. Okay, the arrow hits the center of the target. Assume that the air resistance is negligible and that all the mass of the arrow is at its tip. Show that the time taken for the arrow to reach the target is 1.08 seconds. Okay, so the range, we have to employ the range equation now. Range is equal to horizontal component of velocity. I'm writing it in words, but you can write it in symbols also. Multiplied by time. So this is your simply just R equals to, what was it? 65 cos 4.3 degrees times by, we need to know the time, okay. The range they gave us was 70 meters, okay. So time would be 75 divided by 6.5, sorry, right? No, yeah, 65 cos of 4.3 degrees. So 1.1, wait. 65, 4.3 degrees. Sorry, this was 70, my bad, sorry, 70. Right. 1.079. 9, so basically 1.08 seconds. Calculate the height of the center and the target above the ground. So now we need to see the vertical component of velocity. So first we need to find out S, Y, UY, T plus half A T squared, right? So this would become 65 sine 4.3 degrees times by 1.08 minus half of 9.81 times by t squared, which is also 1.08 squared. So I'll just save it as a value in the calculator, and 65 sine 4.3 times by answer minus 0.5 times by 9.81 times by answer squared. So the displacement that is coming is minus 0.457474 meters. That means from the original location, like from the original level, it's 0.0, that means 0.457 meters below. So we just need to subtract this from 1.66. So 1.66, so height would be 1.66 minus 0.457474. Okay, so this 1.66 plus, this is already negative, so 1.20. Why? Because they're all they're all in 2 or 3 significant figures. So let's keep it into that form. Alright. By considering the energy changes, state and explain how the final kinetic energy of the arrow as it hits the target compares with its initial kinetic energy immediately after the release. a numerical calculation is not required. So as you can see that since it is now at the vertical height lower than the original level, right? So the gravitational potential energy has decreased. And if gravitational potential energy has decreased, kinetic energy would have increased. So that is the explanation in terms of energy changes. So since the target is vertically lower than point of release of the arrow, the gravitational potential energy would be lowered, and wait a second. See, air resistance is negligible, that means the mechanical energy is conserved. Since the mechanical energy is conserved, or you can say the energy is conserved also, so kinetic energy of the arrow would be higher at the target, just before the target, then after its release. Okay. Alright, let's see one more question. Okay, a mass m moves a vertical distance delta h in a uniform gravitational field and gains a gravitational potential energy EP. The acceleration of free fall is g. Use the concept of the work done to show that EP is equal to mgh. So use the concept of the work done. See, this is now slightly different. So work done is equal to force times by displacement. Okay, so you can write it in terms of symbols also. Work is equal to force S, or a better way would be to just introduce the symbols over here. So this is your actually displacement h, or you can say delta h. Okay, force is weight mg, where m is the mass. Mass is already given, so g is gravitational field strength. Okay, therefore, or hence, work done would be equal to mg times by delta h. Therefore, you can write it as w, or we needed to show that the change in gravitational potential energy, right? So work done is equal to the change in gravitational potential energy, work done against gravity, is equal to gain in gravitational potential energy okay. So your therefore the change in EP is your mg delta H. Okay, 0.6 kg mass is attached to a string which is wrapped around the wheel of a generator. The mass is held stationary above the floor. When released, the mass initially accelerates and then falls at a steady speed and spins the wheel. The generator causes a current in a resistor. Okay. Air resistance is negligible. State the main energy change when the mass is falling at a steady speed. So when there is steady speed happening, the change in kinetic energy would be zero. That means there is another exchange happening. So it's no longer gravitational potential energy to kinetic energy, because kinetic energy is not changing, right? That means there is something else happening. So a generator causes a current in the resistor. So the change in gravitational potential energy is actually causing heat. Okay, so gravitational potential energy. We don't say heat energy, we say thermal energy. Okay, alright. When falling at a steady speed, the mass in B falls through a vertical distance of 1.4 meters in a time of 4 seconds. Okay, this causes a current of 90 milliamps in the resistor. Resistance of the resistor is 47 ohms. The rate of work done by falling mass. Okay, so rate of work done is basically power is equal to work done over time so the object is 0.6 kgs, so mgh, 1.4 meters. Yeah, okay, and then time is 4 seconds. So 0.6 times by 9.81 times by 1.4 divided by 4. This is 2.06. 0601. And we need to give it in two significant figures, so 2.1. The power dissipated in the resistor. So I squared R. Okay. So 90 milliamps, so 90 times by 10 raised to the power minus 3 whole squared times by R is 47. So 90 squared times by 10 raised to the power minus 6 times by 47. So this is 0.3807, so 0.38. The efficiency of the generator, so basically power input over power, power output over power input. Power output over power input. So this is 0.38 divided by 2.1. 0.38 divided by 2, and that's just 0.181. So this is 0.18 or 18%. And let's call it a day over here. I hope you enjoyed this lesson. If you have any questions, confusions, or doubts, feel free to reach out in the comments. If you have any specific requests for any other topic that we can do earlier, also you can request that. Also, I offer one-on-one sessions also, where I give the lessons in more detail than this. This is supposed to be just a revision session. However, if you'd like some dedicated one-on-one time, feel free to reach out through the WhatsApp links or the emails or anything. The links are given in the link tree. You can just follow that. And until the next video, take care. Bye-bye.